we'll get started. Just briefly go over what we had seen in the last class. Okay. So, we had divided the number of configurations into two for oblique incidence. We defined what is known as the plane of incidence. It is the two-dimensional diagram that we draw on the paper, all right, describing the interface and the direction of travel, right. And we saw two configurations for polarization which was possible. One where the electric field is perpendicular to this plane of incidence, and the other configuration was magnetic field perpendicular to the plane of incidence. And the previous class we had derived the transmission and reflection coefficients for the electric field perpendicular to the plane of the incidence. Okay. So, this is the left hand side one is known as the perpendicular polarization. We had written the expressions for the incident wave, okay, transmitted and reflected wave, and then we had applied boundary conditions, which means here we have dielectric interface, and we had applied tangential components of E field and tangential components of H fields to be continuous. All right. Once we had the two equations, we solved the two simultaneous equations for gamma and tau. Okay. That is where we stopped. In this class we will go over the other polarization also, and then we will try to mark some inferences from these two derivations, right. All right. So, we will get started with parallel polarization. Here the H field is perpendicular to the plane, all right, and as in the previous lecture, the assumption here is that the H field remains oriented in the same manner for the reflected and transmitted. The electric field will change its direction depending upon K. Okay. So, likewise we had marked E incident to be in one direction corresponding to the right handed triad. The direction of travel is towards this interface. At the origin it gets some portion of it gets reflected, and the reflected wave travels back. Because the K vector is in different direction and the magnetic field is assumed to be in the same direction as the incident wave, the electric field has flipped. Okay. I think the way it has been drawn, it looks like a cross for the HR. So, I will just correct that a little bit. Okay. So, the magnetic field is out of plane and the electric field is oriented in such a way to form a right handed triad. So, the same thing happens for the transmitted ray, all right. The only detail that we need to add is theta t can be different than theta I, and if it is two different media with epsilon 1 and epsilon 2 permittivity, theta t is different than theta I. Okay. So, we will start with writing down the expressions for the incident wave, transmitted wave, reflected wave, apply the boundary conditions. Right. Okay. Once again, the electric field is going to have similar form, right. So, it is going to look like e to the minus j k dot r in medium 1, right. And k incident is going to be kx x hat plus ky y hat plus kz z hat, okay. Or we can write this as beta 1 times n hat, which is identical to the left hand side case, and n hat will have components x, y and z, which can be marked as nx, ny and z, all right. These are identical to the left hand side. So, since everything is nearly identical, right, or everything is identical so far, right, the components will look exactly the same: sin theta I, 0 cos theta I. Remember that we are resolving K vector over here. The K vector between two different polarizations has not changed, all right. It is the same diagram, it is going in the same direction. So, practically there is no difference in the expression for the K, all right. So, here you can write that your Ki directly, I will take the result and say that it is B1 sin theta I x hat plus B1 cos theta I z hat. Okay. Once again, the only difference between the two is the way in which E and H are oriented. Okay. The expression will be Ei exponential minus j k dot r. Right. This is for a plane wave. R is going to be position vector x x hat plus y y hat plus z z hat, irrespective of the polarization. And in the way that we have drawn, the k is oriented in the same direction in both the cases. Only the direction of the electric field is different, right. So, which means that the expression for the electric field is going to look identical. Okay. Okay. The only difference being the Ei naught, right, how it is oriented, etc. Because I have drawn a vector symbol below Ei naught. I think some care has to be taken later on, but for now the expression, the form is going to be exactly same as the other polarization. Now, since this has been established that for the incident wave the form of the electric field expression is identical to the other polarization, it is very easy to say the same thing about the reflected and the transmitted fields also, because the k vector is going this way for the reflected wave and the k vector is going the other way for the transmitted. So, the components of k for the reflected and transmitted will be identical to those cases in the other polarization also. So, directly one could write down the expressions for the electric field to look like what we had for the other polarization. Okay, and I am going ahead and writing down the expression for the transmitted electric field also. Right. Oops. Okay. The next thing that we did in the previous lecture was write down the expression for magnetic field in very simple form. All right. All we did was use Ohm's law to figure out the magnitude of the magnetic field and then write down boundary conditions. Now, electric field expressions are the same, magnetic field expressions are also going to be the same, because you are going to divide each of them by eta, that is it. All right. So, it goes without saying that the form of the incident, reflected and transmitted waves in both the polarizations are going to remain the same. Right. Then where is the difference coming from? All right. The difference is in the boundary conditions. All right. That is where the difference comes. So, we will write down the boundary condition and then we will go ahead and see what the differences can be. All right. So, for both the polarizations, the form of the electric field and the magnetic field expressions are identical. The only change is coming due to the application of boundary conditions. So, once again the interface is at z equal to 0 and apply boundary conditions. Previously, we had the electric field pointing out of this plane, all right, which means that entire electric field was tangential to the interface. So, we had written Ei plus Er is equal to Et. Okay. Now, we have to be a little careful because E is not pointing out of the plane. So, that means that we have to take the component of Ei, which is tangential to the interface, and then we have to apply the boundary condition, which is tangential E field is going to be continuous, right. So, this means that you will have to resolve this into two parts, okay. One which is like this and the other one like this. and you have to take the tangential part, which is the vertical component over here, and you have to apply the boundary condition, that is tangential components will be continuous at the interface. Okay. So, I will go back. The boundary condition here is at z equal to 0. Okay. I have E I naught cos theta I, okay, and the electric field flipped its direction while it is going back. So, you will notice that the vector direction for the incident wave for the tangential component is opposite to that of the reflected component. So, you have to take the difference between the two, right, which is the same thing what we did for the magnetic field in the other polarization. Right. Okay. And in the case of magnetic field, in this configuration, the magnetic field is pointing out of the plane. So, whatever magnetic field you have is going to be tangential. So, the boundary condition corresponding to the magnetic field is simply going to be H I naught plus H R naught is equal to H T naught. The plus sign is simply because the magnetic field does not flip its direction. So, the net magnetic field vector is still pointing out of the plane on the left side and on the right side. Okay. All right. So, now once again you have two equations. The magnetic field can be written as E I naught divided by eta 1, all right, or E I naught E R naught divided by eta 1 and E T naught divided by eta 2. Okay. So, that means you will have two equations, simultaneous equations, and you will have E I naught, E R naught, E T naught to be calculated. Since there are only two equations and three unknowns if you substitute. As in the previous case, you can solve only for the ratio. So, here we will denote the gamma by a suffix representing parallel polarization, right. So, I will mark this as equation number 1, this is equation number 2. You can always write down magnetic field in terms of E I naught divided by eta 1. So, you can always write this down as E I naught divided by eta 1 plus E R naught divided by eta 2 is equal to E T naught divided by eta 2. Okay. So, this is eta 1, right. Reflected is the same. Okay. So, now you will have two equations, and the unknowns that you can solve are only for the ratios. So, the ratio of reflected to incident, right, in this case comes out to be eta 1 cos theta I minus eta 2 cos theta t divided by eta 1 cos theta I plus eta 2 cos theta t. Okay. Okay. Once again, you can solve for the other ratio also, which would be E T naught divided by E I naught, and that turns out to be 2 times eta 2 cos theta I divided by eta 2 cos theta t okay. You do not need to memorize these expressions, all right. Once again, for the quizzes, either these expressions will be given or you will be allowed to bring a formula sheet, right, but the interpretations are important. So, okay. So, now that we have seen the reflection and the transmission coefficient for both the polarizations, it is abundantly clear that there are some commonalities between the two. There are also some distinctions between the two, right. The commonalities, if you look at the reflection coefficient for the perpendicular and the parallel polarizations, the first thing you notice is that the numerator has a minus b form, that is there is a negative sign between two terms irrespective of whether you have perpendicular or parallel polarization, all right, which means that it is possible that under some scenario the numerator vanishes, the reflection coefficient is 0 and the entire wave is actually transmitted, all right. So, the entire wave is actually transmitted and the reflection coefficient is 0, all right. Okay. So, let us take the numerator, okay, and just equate it to 0, all right, and see what is the consequence or what could the material configuration be, right. So, for gamma perpendicular to be equal to 0, the only way is the numerator has to become equal to 0. So, we can say that okay, is there an issue? Okay. For gamma perpendicular to be equal to 0, the only way is okay. Okay. Now, we already know that theta t is dependent upon theta I, and the way theta t is dependent upon theta I is given by Snell's law, n1 sin theta I is equal to n2 sin theta t, all right, which means that for a given material configurations with intrinsic impedances eta 1 and eta 2, it may be possible for us to adjust the angle theta I in such a way that theta 2 cos theta I becomes equal to theta 1 cos theta t. And let us say that in an experiment we do not have control over everything, the only thing we have control over is say the incident angle theta I, all right. And so, let us say that for a particular angle theta I, if this were to happen, what would that theta I be? Okay. So, since this is a special case, we just say that to denote that it is a special case, let us say that a new variable, right, is equal to theta I, okay, theta suffix b equal to theta I. So, this is the special angle at which this numerator becomes equal to 0. Okay. Then what we can do is we can rewrite this equation as eta 2 cos theta b minus eta 1 cos theta t is equal to 0. Okay. So, directly we can say that cos theta b is equal to eta 1 divided by eta 2 cos theta t, or theta b is going to be cos inverse of this angle. So, let us go ahead and write it down, right. All right. So, you take cosine theta t multiplied with the ratio of the intrinsic impedances and you take the inverse cosine, that is the criterion that we need to satisfy at the incidence in order to get no reflection, right. So, this particular angle is known as Brewster's angle. All right. So, this is known as Brewster's angle. However, there are some small caveats, okay, and we will deal with these caveats in a minute now. Okay. Now, let us say that I am going to start with Snell's law again. So, I am having two variables over here. I am having cos theta b, cos theta t. So, on the right hand side I have theta t. I want everything to be in terms of theta b. Okay, I want to get rid of this theta t because theta t is anyway dependent upon theta b. See, by Snell's law, that is it, all right. So, you could write this down in terms of a single variable theta b everywhere instead of having theta t on the right side. So, for doing that you could make use of Snell's law. You can say that So, you can say that n1 sin theta I is equal to n2 sin theta t, or sin theta t is equal to n1 by n2 sin theta I, but I have cos theta t. So, I can do square root of 1 minus sin square theta t, okay, and I can do the same thing for the right hand side. So, I will end up getting square root of 1 minus n1 square divided by n2 square sin square theta I to be the substitution for this cos theta t term over here. Okay. So, I could always do that instead of theta I, it is a special angle, I will call it as theta b and make a substitution in the prior case. Right. Now, there are also other ways to look into it in more detail. In general form, the Brewster's angle is just this much. If you are given enough input, and if you are asked to find out the Brewster's angle, you could find out from the first expression, which is cosine inverse of eta 1 by eta 2 cos theta I. There is no issue at all, right. But doing this gives us some other inferences that we need to talk about. Okay. Okay. The ratio n1 by n2 can also be written in a more complicated form, okay, because we know that phase constant in a medium beta 1 is given by 2 pi divided by lambda in that medium. So, you could always write this down as free space wavelength divided by n1, right. Remember that when the wave travels into a denser medium than vacuum, the wavelength will become smaller, similar to the case with transmission lines where we had see LC on one side to be small, LC on the other side was increased and the wavelength shrunk, the velocity also reduced in the simulations, right. So, similarly, the phase constant in a medium is written as 2 pi divided by lambda in that medium. So, it is lambda naught divided by n1. So, if you were to take beta 2, you will be having 2 pi divided by lambda naught over n2. So, this gives us some idea that n1 divided by n2 can also be written as a ratio of beta 1 divided by beta 2. Okay. We are just substituting for n1 by n2 in terms of beta 1 divided by beta 2. Okay. So, this means that in Snell's law, okay, sin theta t becomes beta 1 by beta 2 sin theta I, all right. This is another way of writing Snell's law. Since we are dealing with a particular angle over here, I will just mark this as B. Okay. So, since we need cos theta t, it is also not unusual to write this as 1 minus beta 1 square by beta 2 square sin square theta b. Could also make a substitution like this. If instead of n1 and n2, you want to make use of the phase constants in that medium, it is perfectly fine, right. Okay. Now, one of the things that we will notice over here is n1 divided by n2, all right, can also be written in other forms. For example, you can write it as a ratio of permittivities and permeabilities. Beta can also be written as omega square root of mu epsilon, right. So, you can always expand these components into more and more constituents and try to look at it more deeply. There is nothing wrong with it, right. Okay. Okay. Now, if I have written it with beta 1 and beta 2, I remember that beta 1 is omega square root mu 1 epsilon 1 and beta 2 is equal to omega square root mu 2 epsilon 2. Okay. Okay. you can always make one more level of substitution for cos theta t, and you will be having square root of 1 minus, right, omega square mu 1 epsilon 1, all right, divided by omega square mu 2 epsilon 2. So, you will get rid of that omega square term. So, you will be having mu 1 epsilon 1 divided by mu 2 epsilon 2 sin square theta b. Then you could substitute that into your expression for finding out the Brewster's angle. It only gets more and more complicated when you make a lot of these substitutions. Okay. But let us go back and look at why we are doing all these things. Okay. The reason why I started with beta and not with n is because simply we remember n to be as square root of epsilon r mu r in majority of the cases. It is only indicative of relative permittivity and relative permeability and permittivity, all right. So, sometimes people tend to confuse as to what is going on. Beta, however, has an expression which is saying that it is omega square root mu 1 epsilon 1. It has the effect of the vacuum permittivity and your relative permittivity, vacuum permeability and relative permeability. So, chances of making mistakes while doing some calculations are a little lower is what I observed. Right. So, once you have something absolute like this, then there are some other inferences that one can start drawing. For example, if you were to take the original expression where we started with numerator of the reflection coefficient is equal to 0, that is where we started this, and we were to substitute, right. So, you will be having eta 2 cos theta b minus, right, I am having minus eta 1 square root of 1 minus beta 1 square divided by beta 2 square sin square theta b. This is the last expression that I have for cos theta t is equal to 0. This is what that same expression would look like, right. So, if you were to remember the previous expression, it is more than enough for you to determine what is the Brewster's angle, but we are just trying to see if instead of writing with terms of eta and theta I and theta t, is it possible to draw some more inferences, that is all, right. So, now one can go ahead and substitute for beta 1 and beta 2 as omega square root of mu 1 epsilon 1, omega square root of mu 2 epsilon 2 in the denominator. This expression starts to look a little bit more elaborate. Okay. All right. So, there is also another thing that we can do. We can substitute we already know that eta 1 is square root of mu by epsilon 1, eta 2 is square root of mu 2 by epsilon 2. You could also make the same substitution for eta 1 and eta 2 in that equation. That makes it look even more complicated than what it was before. Okay. If you do these substitutions and if you wish to solve for theta b, you will get a very large expression. Okay. I will not do the solving part, alright. I just plugged it into Wolfram online and I got a solution for theta b which seems to match with the expressions that people have been mentioning in the textbooks. I will write down the expression I got from Wolfram. Right. So, I got theta b is equal to tan inverse square root mu 2 by mu 1 times square root of mu 2 epsilon 1 minus mu 1 epsilon 2 divided by mu 2 epsilon 2 Okay. This is another expression that you can write for your Brewster's angle. The simplest expression is what we had before. If you know that, you are all set, right. So, given a problem configuration, if you are asked to calculate, you know how to calculate, all right. This is just to see in which cases this Brewster's angle can exist, in which cases it cannot exist, etc. Okay. Now that we have written this, right, we can do the same thing for the other polarization. So, for gamma parallel to be equal to 0, we can take the numerator of the expression for the reflection coefficient and equate it to 0, right. So, we can write eta 1 cos theta I minus eta 2 cos theta t is equal to 0, and then you make the same assumptions. Let us say that in an experiment you do not have a control over everything, but only the incident angle, and let that incident angle, which is a special incident angle where the reflection coefficient becomes 0, be known as theta b. Then you will rewrite as eta 1 cos theta b minus eta 2 cos theta t is equal to 0. This implies that theta b is equal to cos inverse eta 2 minus eta 1 cos theta t. This is the simplest expression that you can use to get theta b for both the polarizations. One of the things that we notice here is that because the numerators for the reflection coefficients were different for both the polarizations, the angle at which the reflection coefficient goes to 0 is also slightly different. So, if you notice that in the left hand side case, you had cos inverse of eta 1 by eta 2 cos theta t. In the other case, you have a different ratio. So, you have 1 divided by. So, the angles at which the reflection coefficient becomes 0 for different polarizations is different, all right. So, this is also known as Brewster's angle. The only thing is the Brewster's angle is also polarization dependent. If you have perpendicular polarization, you have to use one expression. If you have parallel polarization, you have to use some other expression, which means that when we are talking about Brewster's angle, we also have to indicate the polarization for which the Brewster's angle is calculated, all right. So, likewise you can say that this is perpendicular, this is parallel. Okay. So, Brewster's angle for perpendicular polarization, Brewster's angle for parallel polarization, this is how it is usually expressed. Okay. Now, we can go through the Snell's law, make substitutions for eta 2, eta 1, make substitutions for theta t in terms of theta b, all right, and you could make substitutions in terms of beta 1, beta 2, then make it to epsilon 1, epsilon 2, etc. It is the same drill over here, right, except that the angle here turns out to be slightly different because our starting expression itself was different, all right. So, to indicate that we are dealing with parallel and perpendicular cases, so I am just writing a suffix of perpendicular and parallel. Turns out that theta b is tan inverse of square root of epsilon 2 by epsilon 1 square root of mu 1 epsilon 2 minus mu 2 epsilon 1 divided by mu 2 epsilon 2 minus mu 1 epsilon 1. It is a very big expression. I do not expect you to remember all this, right. If you are able to do the first case, which is this cosine inverse of eta 1 by eta 2 cos theta t, etc., it is more than enough. So, there is a slight difference between these two expressions. Right. And one can pay some attention to these slight differences, all right. One of the things that I have touched upon in the past lectures is mu 1, mu 2 being not the same as vacuum permeability and permittivity permeability. So, mu 1 and mu 2 are permeabilities, all right. You can write them as mu naught mu r, okay. However, in majority of the materials there is no magnetic properties magnetic materials are rarer than the other dielectric materials. So, it is quite possible, right, that for majority of the materials that you will encounter, mu 1 and mu 2 is equal to mu naught. All right. In general case, this is the expression for your Brewster's angle for perpendicular and parallel polarizations in the most expanded form. Suppose you are not given anything except mu 1, mu 2, you will be able to do this. All right. All right. Notice that this expression has got nothing. You just need mu 1, mu 2, you will be able to find out the expression. If you were to go back, incident, suppose your transmitted angle is given to you, right, then you will be able to find out the Brewster's angle in the other case. But if nothing is given, you will have to do some arithmetics, but it is possible to write down the incident angle purely in terms of material parameters and arrive at what is the Brewster's angle. Okay. Now, this is the final expression, but one could also go one step further and make it a little bit simpler for many people, in the sense that majority of the materials I am just writing majority of the materials, not all materials have to undergo this. So, this is the expressions that we have got is final and it is correct, all right. But in case you want to make some other inferences which are more common than some other cases, right, you can say majority of the materials have mu 1 equal to mu 2 equal to mu naught. So, that is you do not have any magnetism related properties in these materials. So, vacuum permeability is the same as the material permeability, or mu r is equal to 1. It is very common for most of the dielectrics, most of the metals also you will find that mu r is equal to 1. Okay. Okay. What then ends up happening is, if mu 1 is equal to mu 2 is equal to mu naught, you can always go back to the final expression that you have, substitute for mu 1, mu 2 as mu naught. Okay. The first thing you will notice is on the left hand side over here, this ratio will become 1, all right, and then you will have mu naught epsilon 1 minus mu naught epsilon 2 divided by, no, you have a mu naught epsilon 2 minus mu naught epsilon 1, right. Okay. Now, you can take mu naught common from the numerator and denominator, and you will just get a ratio which will look like square root of mu 2 by mu 1 is just 1, all right, and then I make a substitute for mu 2 and mu 1 to be mu naught. So, I can take mu naught outside, right. So, I can just say that, just do like this, right. So, it is epsilon 1 minus epsilon 2 divided by epsilon 2 minus epsilon 1. Once again, I can take a minus sign, all right, the ratio has to be equal to minus 1. So, I get tan inverse of minus square root of mu naught, right. Okay. Tan inverse of square root of minus mu naught is what I would get. Okay. Generally, tan inverse of a square root of minus mu naught means that you do not have a angle that you can, attach to theta b perpendicular. So, tan inverse of square root of minus some quantity means the tan inverse of j something, right. So, there is no real angle theta b which will give you this relationship, all right. So, people argue that in the case of perpendicular polarization for non-magnetic materials, you may not have a Brewster's angle. Okay. So, in the case, so there is so many conditions. In the case of perpendicular polarizations, if you have non-magnetic material on the left and on the right, you may not get a theta b perpendicular, because you will end up having tan inverse of square root of minus mu naught, all right, minus 1, all right, whatever. Okay. So, it is mu naught is common in the numerator and the denominator, is it not? Okay. So, it is tan inverse of minus 1 within a tan inverse of square root of minus 1. So, it becomes tan inverse of j, right. So, it becomes tough to find out what this theta b perpendicular is. So, in case of planar angles, it is not going to be possible. There are some other arguments. You can say that you can say that the angle is out of plane and all that. So, if you have the entire diagram in plane, you can always argue that if you shoot the beam out of plane, you will get something else, right. But we are not getting into solid angles. Okay. So, it is not possible to find out a real angle theta b perpendicular. So, people tend to say that for perpendicular polarization, Brewster's angle does not exist. Okay. But it is under the assumption that you have non-magnetic materials. Right. Now, how about we apply the same condition to the right hand side? Okay. So, for mu1 equal to mu2 equal to mu naught, theta b parallel is tan inverse square root epsilon 2 by epsilon 1 times mu naught epsilon 2 minus mu naught epsilon 1 divided by mu naught epsilon 2 minus mu naught epsilon 1. So, that ratio becomes 1. So, I have tan inverse of square root of epsilon 2 by epsilon 1. Since in majority of the materials you could have epsilon 2 different than epsilon 1. So, you can say that theta b parallel is tan inverse of square root of epsilon 2 by epsilon 1. So, if you consider majority of the materials to be non-magnetic, okay, then for a particular polarization, you may not be able to find out a Brewster's angle, but for a other polarization you will be able to find out a Brewster's angle, which means that for a given material configuration that is non-magnetic, the interface will have reflection coefficient being equal to 0 for some component of the electric field that is parallel, that is in parallel polarization. But if your incident wave is going to have some other polarization, it may have some reflection coefficient coming in. So, the polarization plays a major role at the interface, okay, in determining your reflection coefficient. This aspect is very different from transmission lines. In the case of transmission lines, you strictly had eta 2 minus eta 1 by eta 2 plus eta 1, or equivalently we wrote it as ZL minus Z naught by ZL plus Z naught. If your material properties dictated ZL, Z naught, etc., then you are pretty much fixed. Whatever voltage and current waves you are launching will adhere to this ZL minus Z naught by ZL plus Z naught. But in this case, merely the material configuration is not enough. You also need to have the polarization being aligned in some direction, all right. So, it has to be parallel polarization in the case of non-magnetic materials to have reflection coefficient equal to 0. Okay. So, this means that impedance matching in the case of electromagnetic waves should also consider polarization. Okay. It is perfectly possible to have no reflection of one polarization, but a lot of reflection of the other polarization. It's perfectly possible, all right. So, that is what it is going towards. So, impedance matching in the case of electromagnetic waves having oblique incidence on interfaces is not a very simple problem. Okay. Now, this has a lot of practical applications. Many of you, when you buy eyeglasses, they ask for some anti-reflection coatings, etc. Essentially, what they are trying to do is make sure that you get a lot of light inside, but you could also look at it as another problem. You could say that there exists some angle, Brewster's angle, for the light that is coming into your glasses. You do not want any light to be reflected from the glasses directly, because it needs to reach your eye. Okay. So, you can say that I do not want reflection, so I want to put some coating there. You could also determine what could that, you could say that epsilon 1 and mu 1 correspond to air, epsilon 2 and mu 2 are corresponding to some material that you are going to be coating. You could calculate a Brewster's angle. You could say that for this angle, a lot of light is going to be coming in. That is only for one polarization. For the other polarization, it is not going to be working very easily. So, you will need a more complicated, coating for your glasses, all right. So, impedance matching in the case of EM waves, it is not a very easy thing to do, all right, unless you have very good control of the polarization, etc. It is a disadvantage in that case, but it is also an advantage in some other cases. For example, if you are driving, all right, or if you are outdoors, it seems that the polarization of glare, okay, coming from natural sunlight is very different from the polarization of useful information that is also coming from these materials. So, you will have glare cutting glasses, okay, or polarizing glasses, etc. So, it is also possible that you have reflection coefficient 0 for the useful information to come in and reflection coefficient not equal to 0 for the glare part that is actually coming into your glasses, right. So, it could be used in useful ways, or it can become a disadvantage when you are actually trying to solve problems. So, the only thing that I can say at this point is impedance matching in the case of electromagnetic waves is non-trivial, okay. Using just manipulating angles, you need to do something else, right. So, I think we will stop here. One of the reasons why I mentioned these is because in the case of transmission line, impedance matching was trivial. All you needed to do was find out ZL minus Z0 by ZL plus Z0 and then make sure that you go to the center of the Smith chart somehow, okay. Here, however, if you go to the center of the Smith chart for one polarization, you may not be at the center of the Smith chart for another polarization. So, it becomes very important to draw Smith chart for different polarizations and then decompose every incident wave into a parallel and a perpendicular component. Strictly a E field need not be parallel or perpendicular to the plane, it can be anywhere in between. Those cases you will decompose it into two, and then you will have reflection coefficient for one component being some value, the other component being some other value, and then you have to take the summed up effect. So, effectively what we are saying is polarization is a very important property. In the next class what we are going to do is account for polarization when it travels from one medium to another medium, okay. So, here we have made an assumption that E field is perfectly perpendicular, in the other case it is perfectly in plane, it has components. What if it is in between, okay, what happens, and what happens to say linear polarization, circular polarization on the interfaces, what can you expect. So, these are some things that we are going to see, okay. So, for now I will stop.